Hey, I know a lot of you. My name is Summer. I work at Scale, running the research teams here. And today with me, we're excited to have Jimmy Ba and Noam Brown. Let's start with Jimmy. Okay, Jimmy is one of the co-founders for XAI, building the truth-seeking AI. And before XAI, Jimmy was actually well known for his work inventing the Atom Optimizer, layer normalization, and also was one of the early pioneers of model distillation. Let's give a round of applause to Jimmy. And then we also have Noam here, who is a research scientist at OpenAI. He's most well known for his early work in creating the superhuman poker players with models. And recently, like 2 years ago, Noam also built the first LM agent that's used to be as good as humans in the strategic game of diplomacy. And most recently, Noam is also one of the co-creators for the famous OpenAI O1. So super excited to hear from Noam on some of his thoughts in LM reasoning. Let's get a round of applause. So maybe we can start with a quick warm-up question for both of you. So we all know that language models have gotten a lot smarter over the years. We'll be curious to hear if you can share some of a key moment where you observed a language model like doing something that surprised you, like a reasoning task that first surprised you, either like good or bad, and whether that moment has shaped any of your thinkings moving forward.
Want to start?
Yeah, sure. There's one more question. I don't know, like I'm like a dinosaur in this field now, right? So being around for so long, I actually one of those like LM deniers, the nice layers, early on, until the moment of I think that was like right after the NeurIPS deadlines of 2022, and one of my students, Karen, he showed me this paper. Oh, he didn't really show me a paper. He showed me this console. It's like OpenAI Playground. I was like, what is this? And then he typed in a question. The model doesn't do much, right? And then he's like, you should try it. Just ask it to think step by step. I was like, okay, step by step. I was like, damn. So that was like the first moment I think like the model being not lazy, and that was very surprising. And that I think this theme of not being lazy is gonna come back over and over. Like the model currently is dumb/lazy, and a lot of that is just like, and that was the first moment. Well, maybe the model is not so dumb and not so lazy, and there's some spark of intelligence there.
Yeah, so the model is lazy and dumb by default, but when you ask it to be not lazy, like let's think step by step, it gets a bit better.
Oh, you have to try so hard.
For me, I guess I was surprised early on at how dumb these models are. My go-to question was always tic-tac-toe. And so when like GPT-3 comes out, GPT 3.5, I always ask it, okay, let's play tic-tac-toe and see how far it gets through the game. And it just completely fails. Like the early, like GPT 3.5 couldn't even draw the board correctly. And GPT-4, despite being like a pretty smart model, it still makes obvious mistakes. It makes illegal moves. It doesn't recognize when it's won or if I've won. And so for a long time, I was thinking, like, how are we going to get from GPT-4 that can't even like draw the board for tic-tac-toe to something that's actually super intelligent? I mean, yes, it's getting better as you scale up. I mean, now at least like, it's getting better at drawing the board and makes fewer illegal moves. But if it's not even going to be able to figure out how to win at tic-tac-toe, and we've got like 4 more orders of magnitude scaling left before like, we get to unreasonable amounts of pre-training. How are we going to get there? So I remember like I would talk to people that were really bullish on AI, and there were some people that just said like, it's okay, tic-tac-toe isn't, is not really representative, and you just scale up pre-training and you'll get there. But I remember I had a conversation with Ilya actually in like late 2021. And, he asked me what my AGI timelines were. And I told him like, I honestly, like, I'm kind of skeptical because I don't think pre-training alone is going to get there. And having worked in games, I saw how much inference compute mattered. And I said, like, until we figure out how to scale up inference compute for language models, we're just not going to get to AGI. And I feel like that is a very hard research question that might take a decade or more to figure out.
Oh, this conversation was recently, or
this was in late 2021.
Late 2021.
Yeah.
So a lot of foresight to have seen inference time compute coming at that stage.
Well, I mean, my whole career was working on inference time compute for various domains, and at that point it became clear, like, once LLMs were taking off and they weren't using it, I was like, okay, well, I've seen what happens when you don't use these in games. When you don't use large scale inference compute in games, and it doesn't get you very far. To my surprise, like, Ilya actually just agreed with me, and he was like, yeah, we absolutely need to figure this out. And I do think that there were quite a few people that recognize, when you talk to them in detail about how are we actually going to get to super intelligence and these kinds of things, that they recognize that the current paradigm wasn't going to get us there, and that we needed something more. And I think maybe I was a bit pessimistic on how long it would take, but I think we've got all the pieces now. So I've gone from an AI skeptic who's like, okay, yeah, this is not going to happen in the foreseeable future, to somebody that now I see the path forward.
Very cool, very cool. There's been a lot of different ways for language models to get really good at reasoning capabilities. And the standard ones are just upping the compute, like train a bigger model, train with more data. I think, Jimmy, you have done some work that's slightly different, where you're teaching the model to give a more useful prompt, where you describe the task better. It's called automatic prompt engineer. Do you want to tell us a little bit about that?
Yeah, sure. I don't think it's any that different. Like I just in general, like now I'm in the state of in the scientism state that if you're at the right place, the right time, with the right tool, with the right resources, any smart people is going to come with the same ideas. So that paper was really just like, after we start prompting the model, we thought, well, we're in academic. We don't have compute. Like, what are we gonna do? If you're the lab who's studying like the inner workings and mechanics of deep learning and neural networks, and now all of a sudden they took that machine away from you, you're like, well, so what are students gonna do? So that really is a starting point. We're like, well, the prompting is interesting, right? Because the only tunable parameters of those systems, right? If someone instead of you building your own machines, you're tuning the knobs of someone else's machine, but you can't even look inside. Like, the only parameter you can set are those prompts. So we're like, well, what would be the equivalent of like the gradient descent of 21st century, of like tuning those knobs to be really good? So the starting point is like, well, can we just recreate like an Adam equivalent of how you can tune those prompts? But then instead of Adam, we got Ape, because those machines were so dumb and so lazy. So Ape as in like automatic prompt engineering. So the gist of how it works is like, so the idea of like, how can you make the machine do better if you can only tune the prompts? I think the one-line description I think everyone can understand is, imagine you want to teach a machine to do something, or teach your intern, right? That's probably the best analogy. So, and you have all your internal company stacks and tools that, it's really hard to describe to your interns in words. So how would you do it? Day one, your intern come in. So the way I would do it is like, all right, intern, come sit next to me. I'm gonna do some demonstrations right in front of you, right? And afterwards, it'll be like, all right, make this run faster. That's it. So that's essentially the core idea of the paper, is you take some demonstration, so the model kind of sees like what those tasks are, and internalize in its own way, like, what kind of system prompts it needs to describe those tasks without seeing those demonstrations. And then you tell it, do it way better. So now that's how you teach a human, right? So that's kind of like the starting point and the core idea of the paper. We try tons of things, including a lot of the tests on compute, like how can you, like, we tried all the best of ends. We even tried some crazy, like, linearized search where like, oh, this is the previous system problem. Now can you modify it, right, by adding the words of alternatively, wait a second, but, I wonder. And then the model was so lazy, just couldn't do it. So in the end, we just went with the best of n stuff. But yeah, so that was kind of the beginning. I think now we have a lot more advanced systems that can look at a task, look at some collection of system prompts, and make new system prompt for a task now being deployed in as what's called meta prompting in like ChatGPT and cloud called like prompt generator. So yeah, I think the field is definitely moving towards the right direction. That's where, that's the next generation gradient descent, pretty much.
I thought a super interesting figure I saw from that paper was the models. If you just have a human come up with a prompt that we think would work well, it's actually pretty counterintuitive. It doesn't work very well. Like the one that the model ends up optimizing and lands with, it's like pretty counterintuitive. It's not something people would say.
Yeah, I mean, that's also like one of the things why we believe this technique and could and should and probably must work before we reach AGI or before we reach like ASI is that the models probably has some internal workings that you try really hard to align those models to be like human, right? But there's always going to be this gap. So if you can run gradient descent on the system prompts to modify it over time, you're arbitraging this gap because model probably has this internal language. It knows how to activate certain capabilities and tasks, right? So if you believe that the model, there's always going to be this alignment gap, then there should always be some hidden prompts in there that enlist some even crazier capabilities and make the model just all of a sudden do a lot better in certain tasks. And turn out, yes, if you just spend tons of task time compute, by doing dumb best of n, just keep sampling new system prompts to describe the task, and all of a sudden you're gonna be like get prompts that's so counterintuitive that no human will ever write. So how fast we can get to AGI is going to be like how fast we don't have to do any of the meta prompting, right? So all you need to, with all the personalizations, I think the proper way to solve this task, I think is if you're in a company has ability to build those systems and has ability to observe a user over a really long period of time, then I think this alignment gap is going to shrink. Because you get to know the user, you get to know like what they like, how they want to prompt the system, and things like that. Then in the end, the user, all they need to do is just like make this better, and the model obviously knows exactly what to do.
Last question on this topic before moving to Noam is, do you see this direction as like a similarly as important of a direction as say inference time compute or the fine-tuning paradigm, or is this more of a like we tried something with prompting, it works really well, but this is probably the best we can do?
Yeah, I actually think like before we completely close the alignment gap, we're gonna get through a stage where the system is gonna look like multinational corporations. You're gonna have like interns, intern managers, FTEs, skip managers, and CEOs, right? And then how are they gonna solve the task together, right? It probably has to do some sort of prompting, right? Tuning each other's knobs, but you cannot really peek into someone else's brain, right? And imagine so think about when you're instructing your intern, right? You probably thought really hard how to motivate them, how to prompt it, how to set up the goals. Like this is benefit the future of humanity is that if we don't do this, the world is gonna end.
That's certainly what I do with all my interns.
Right, and all of a sudden they get 20% productivity buff. So, yeah, it's gonna be very similar.
Awesome. Noam, would love to hear a bit from you on. You have a ton of experience building game-playing agents from poker, multiplayer poker to diplomacy, which is a lot harder because it's not just a zero-sum game anymore. It requires players to actually collaborate with each other and collaborate with humans. And from the game-playing agents to now the amazing work with OpenAI 1, I'm curious to hear your observation on some of the historical trends in your head, right, at the high level. What does the trajectory look like? And any insights you can share along those lines?
Yeah. So I started my PhD in 2012 working on AI for poker. And when I started, the attitude was that we had the algorithm and we just needed to figure out how to scale it up really well. And so the first 3 years of my PhD was focused on scaling up this algorithm by about 100x It was called counterfactual regret minimization. That algorithm, it's not too important today, but it was very useful for poker. And it's kind of like pre-training. We would do self-play, so we'd have the bot play against itself. And every year there would be this competition, and the bot, we would do self-play across thousands of CPUs for months, like 2 or 3 months. It's a lot of compute for academic standards. Today it's nothing. But and then when it came time to actually play, the bot would act basically instantly, like 10 milliseconds to look up what it should do in a particular spot. And in 2015, we did a competition where we played against the top poker pros in the world, and we lost. And I noticed when we were playing that the humans wouldn't act instantly. They would take some time to think through hard situations. And that inspired me to investigate this a bit more and see, okay, how much of a difference does this actually make? And it's not that people hadn't investigated how to do, deeper thinking at basically search or planning. People had investigated how to do this in poker, but it wasn't really considered a high priority for various reasons. And it's difficult. It's not very fun to have a bot that will take like 20 seconds to make a decision in poker, because you have to play. Poker is a very high variance game, so you have to play a million hands of poker to tell whether your bot is beating the other bot or the human. Then you don't want it sitting there for 20 seconds each hand to make a decision. And anyway, what I found is that when I had the bot think for 20 or 30 seconds before acting, it was the equivalent of scaling up the pre-training by 100,000x. So in this one result, the first 3 years of my PhD, I managed to scale it up by 100x, which was, I thought, very impressive work. I published multiple papers on that. And then in this one result, I managed to scale it up by 100,000x, the equivalent of 100,000x, by just having it think for 20 seconds before making a decision towards the end of the game. And for me, that was really a wake-up call that, okay, we were taking the totally wrong approach. And instead, I focused my research from that point forward on how do you scale up search and planning in poker. And we did another competition about a year and a half after the first one where we lost. And this time we crushed the humans. We beat them all 4 of them individually. And so that was the first moment for me when I realized, like, okay, there's something powerful here. We did a follow-up competition that was 2-player pokers. We did a follow-up competition a couple years later for 6-player poker. And this time I focused even more on, like, how do you scale up search? How do you make it more general? And we again beat the top humans in 6-player poker. And this time the bot cost only $150 to train, which I think really shows that this wasn't like due to compute growing over time or anything. This could have been done in the 90s if people had known to focus on search and planning and scaling inference compute. And I think the real takeaway for me is how, for me, I after this, I just basically, like, all of my research, people were trying to throw model-free deep RL at various domains like Hanabi and diplomacy. And I would just try to figure out how to scale inference compute and do search and planning. And it would always just blow all the existing techniques out of the water. It's interesting to me because, like, people are always, like, kind of skeptical of it. I didn't really see other people, like, picking up on this and trying to do these kinds of techniques in other domains until they saw it being really successful in a domain that they cared about. Like, I worked on Hanabi bots, which Hanabi is this cooperative card game. It was a popular benchmark for a while in the RL community. And, my collaborators, when we figured out a very simple search technique that would just think for, like, basically 1 second instead of, like, 10 milliseconds, they thought it was a bug. The performance was so good that they thought it was a bug. And so I think the reason why this took so long for poker and also for other domains is that people just didn't appreciate how much of a difference it would make. Like, if you had asked me before I saw the results in poker how much of a difference it would make, I would guess something like 10x, which is big, but I'm not going to, like, pivot my whole research agenda to focus on this. If I had known it was 100,000x, I would have pivoted a lot sooner. And by the way, this result is not unique to poker. If you look at Go, AlphaGo famously beat Lucidol in, like, this landmark achievement in 2016. But if you look at just the raw neural net, it actually loses to top humans. What is superhuman is the raw neural net plus Monte Carlo tree search. And if you take out the MCTS, it doesn't beat top humans. And if you look at how much you would have to scale up the model and training to get just the raw neural net to beat top humans, or to match the performance that you get with full AlphaGo, it would be about 1,000 to 100,000x. So the fair criticism to all of this has been that the techniques that we used in poker were somewhat specific to poker. The techniques that were used in other domains were somewhat specific to those domains. And the beautiful thing about neural nets is that they were always very general. DeepRL, model-free DeepRL, is really general. And so, yeah, around the time I finished working on diplomacy, which again, we developed ways to scale up inference compute that was specific to diplomacy, I realized, okay, the way to really have a big impact is to scale up inference compute in a very broad, general way that works across almost all domains. And that's what I was interested in when I joined OpenAI. Fortunately, people at OpenAI were also interested in this direction, and there was a very strong team that I was able to work with to make it happen. So that's one. I hope you all enjoy it.
So I think one question I have about this is, you were mentioning that the raw neural net is not that good on its own, but with the search on top of it, it's much better. What stops people from just, distilling from the model plus search results, put it back into the model, and just iteratively and continue doing that? Do you hit like a plateau at some point, or not?
That's a great question, and that's a common criticism that I got when I was pitching this direction to people. And my response to that is, if you look at what AlphaZero and AlphaGo are doing, it is exactly that. It is doing search, it's finding a policy, it's finding moves that work, and then it's trying to distill those moves into the raw neural net. And the evidence is there that if you just look at the performance gap between the raw neural net that's distilling all those, all that planning and search, and compare it to that plus the search, it's a huge difference.
So empirically, it just it doesn't fully work yet.
I'm not saying that it's not possible, but I'm saying that if you look at AlphaGo and AlphaZero, which was one of the inspirations for me, that that's literally what the algorithm is doing, and you're not able to distill the performance into the raw neural net.
Very interesting. So guessing if you have like a much bigger, more powerful pre-trained model, it's
exactly
possible.
Yes, and that's exactly that. Yes, in my view, it's a model capacity issue, and so the response to that is then like, okay, well, could you just have a bigger model? And then yes, the answer is yes, but how much of a bigger model would you need to have? And how much longer would you need to train that model? Mm-hmm. So everything could be done. I fully believe that you could just scale up pre-training and get to super intelligence. But how much would you have to scale it up by? That's the challenge.
Jimmy, you're still spending a lot of your time fine-tuning models. So I'm curious to hear your thoughts on the inference time compute paradigm.
Yeah, I think it's amazing. So it's, I guess like we kind of moved from like the compression machines era to like thinking machine era, and people were asking last night what does it take to make the model run search and contemplating things for millions of tokens. I think you can already do it now. You can already do it yesterday, last year. Just the model wasn't making much progress, right? That's the main problem. And I think a lot of this running search in the test time, I feel like it's like, the way I think about it is, what do you want to do? You want to solve a problem. If you want to solve a problem, how much compute are you willing to spend on the solve of that problem? One problem, not all possible problems. Mm-hmm. So in the compression era, you pour in like ungodly amount of compute into like this giant neural networks, but the actual amount of compute to solve a problem, amortized across all problems, is a giant number divided by infinity, 0, right? So and now we're like, well, how can we make it non-zero? And of course, you're gonna see like a huge boost of like 10x, 100x, 100,000x, right? And I think that's probably the way to think about it. It's like if you were pouring compute to solve a problem, where do you want to pour the compute? Right, and I do echo like Noam's thoughts on like if we do compression really well, you can probably get there. And then still, I actually have a question for you afterwards. Yeah, so right, because I think the intuition for compression is big fan of the poker work, by the way. So you can think of like the test time is like you're building a tree, right? Although it's like linearized and a bunch of words, but you can kind of visualize this as a kind of tree with a lot of nodes. And the question is, how many bits do you need from the base model to actually make to go down the correct branch, right? How many residual entropy are there you need, right? So the way to think about it is like, well, at each of the branch, you have some high confidence this has to be the right next move versus here's a collection of, 2 choose 1, right? Now you have one additional bit of entropy that you have to resolve before you actually can go down to the model will automatically go down to the correct path. And if you think from a compression path is you take the best trajectory and you ask the model, what's the log likelihood of this trajectory? That essentially tells you how many and then you only calculate maybe like, not all the words, right? Because the words can be different. You have surface form competition, but you only say like, well, if you can like kind of conceptualize as like, how many additional, cross entropy loss are there for the model to pick the best perfect reasoning chains? Maybe like, in the current model, there's like 4 bits remaining for a very simple toy search problem. If you 100x compute, there's probably 2 bits remaining. So that means you remove half of the model is able to actually correctly identify some of the branches already if you 100x the compute. So every time, because it's a log linear curve, right? Every time you 100x, you get rid of 1 bit almost. So then the question is that for some really hard thinking problem, how many remaining bits are there? And do you actually want to do it in a pre-training? Or do you want to do it just by collecting tons of data, just very specialized for, that relies on the model to like backtrack itself and fix, and how many bits can this backtracking business fix? So the answer is like, you have to do both, I think. I still believe that although the model is very lazy, but through ape, right? The lazy, I'm here determining formally define that as, if you ask a model to do something, it just gives you the answer right away without any thinking, right? So, but I see the Einstein in the model, right? So just from I think there's Einstein living in the model that you just have to like get them out, right? So the best pre-trained model is absolutely crucial for you to get rid of some residual bits that even for humans is really hard to identify which search branches go down. So you have to combine the absolute best world model, compression model to, on average, hammer out all the different, remaining bits, and then you get some world experts to tell you, oh yeah, for this problem, I know this is the branches to go down, and you record that and train it, and you run it in the test time for that particular problems, and all of a sudden you get like 100x, like 100,000x improvement. Yeah, so it's great. But here's a question: when do you think will be the first year? If you knew what we knew today, what would be the first year we could build O1?
Oh.
Sorry, if we knew
like all the techniques, internal workings, how to build those systems. Like, what would be the first year, like given the compute we have, that we would even have a chance to attempt a project like O1 in history?
Oh, in history. I don't actually think it would be pretty recent because I think what's really powerful about O1 is the generality, and I think to have that kind of that generality, you do need pre-training to achieve a certain level of performance. And so I think it could not have happened too much sooner, simply because pre-training would have been the bottleneck.
Right. Yeah, I 100% agree. It's like having whoever has the best pre-trained model is gonna have such an easier time to hammer out those remaining bits in the search tree. And also right now we're kind of in like this, maybe like you don't agree, but I kind of feel like we're still in this AlphaGo era, where analogous of AlphaGo is like you have You build up the scaffolder system, you can run it, but the whole thing is bootstrapped and kindled by a human, SFT. And then there's probably somewhere in the world, in some corners, people are thinking really hard about how do you build AlphaZero of those systems without any of the human kindling. Agree, disagree?
I think there's a lot of people think about that, yeah.
Okay. Right.
Yeah, so, oh wow, we're very short on time. So we've heard a lot from Jimmy and Noam on what they have thought. I think it would be great to also give an opportunity for you to call on the audience on something that you would like to see research, maybe like evaluation methods, benchmarks, or just different directions of research that you would love to see more from the audience. If you were to say like one or two, what would those be?
I think certainly evals. I mean, I don't know if you want to talk about evals, but like, yeah, I think one thing that I don't see enough research on is more about like the societal implications and what I don't see economists publishing research on what economics looks like in a world where there's actually really capable AIs, general AIs. What are the implications of large-scale inference compute being a major factor? And I think a lot of the safety work that I saw assumed a world where it was all about pre-training. So you spend tons and tons of money and compute on pre-training, and then inference is negligible. And so in that case, for example, everybody has, you train this huge model, and then in theory, like everybody could have access, it could have the weights, and then they could all have access to the super powerful model. I think that world, if the inference scaling continues to be the path forward, or a path forward, inference compute ends up being very valuable. And so what does that world look like where just having the weights isn't enough? You also need to have a lot of inference to actually run it. I think there's a lot of questions around what that world looks like and how to structure things so that we achieve the best outcome possible that I don't think I see a lot of people outside of the AI community really thinking about. And I think that would be really valuable.
Also, I guess policy research, it's much easier to take the open source weights and study the hell out of it and measure everything you can measure. But there could be, people using it very differently, leveraging the inference time compute, and you can't really predict very well like how powerful the entire system is.
Yeah, certainly what this means is that any open source model is a lot more powerful than, just what the raw model capabilities appear. Yeah.
Really good point.
I don't know. You guys need to build like a humorous leaderboard, like the fun eval.
The fun eval.
Yeah, that's right. Yeah, I think that's like the number one quintessential thing, right? The robots today is just so boring. Like, the scientist and Adam joke is like, that should be the cardinal sin of like, if you do that, it's like ELO minus 1,000, right? So, yeah, so
that's true. If you ask a model to tell you a joke or something, everyone can try it now. It's either going to regurgitate something that's already out there that's funny, or it's going to say something entirely not funny.
Yeah. Well, it turned out we already have the best, fun humor evals, right? Just like, put our latest models on stage, right, to see if it bombs or not. It just like operationalize this so we can all participate and to see that's I mean, if the system cannot make human laugh, then what are we talking about alignment?
Right. Yeah, I guess we do build a lot of evals at Scale. We have the Scale leaderboards. I would love to get maybe a show of hands from the audience if you would like to see like a humor leaderboard coming out in the near future. Raise your hand. Let's see what the demand is. Okay, we'll build one.
Okay, all right, let's go.
All right, thank you so much, Noam and Jimmy, for joining us for the session. Thank you all.
Right, thanks.